Hello friends, today we'll be starting with the module on internal flows. We understood that external flows is where there is a body and the fluid is flowing over it, so the body is surrounded by the fluid. In internal flows it's just the opposite, so you have a bounding surface and the fluid is flowing inside it, so it's like flow through pipes or ducts and various such things. So the difference here is that there is a solid boundary that is bounding the flow, and the flow is confined to those boundaries. That is the difference between external and internal flow. The wall shear stress has a very similar mechanism, of course, because there is no slip at the wall, and therefore the fluid that flows over it will have a zero velocity with respect to the wall at the surface, and there will be a gradually increasing velocity as you go away from the wall. So something like the formation of a boundary layer on each wall would happen. So even if it is a pipe and there is flow going through the pipe, at all the walls of the pipe you'll have a similar behavior. Say for example, two parallel plates and the flow is going between the two parallel plates. There can be a boundary layer development from each of those parallel plates. So that's a fundamental building block which we can use from the external flows, but the characteristics of internal flows are substantially different from those of external flows, so we need to understand a few new concepts about internal flows as well. Okay, so that's the ambit that we will start with, and as before we will start with the fluid flow. We will consider the heat transfer after we have done the fluid flow solution. So, and again we will not be solving any equations, we will be using the same equations that we derived in the last module. From the Reynolds transport theorem we derived the conservation equations for mass, momentum, energy. We will be using the same equations, and we will be looking at the concepts of full development or developing flow, which is the new concept that will come into place in the topic of internal flows, which we have not done in external flows. So let's understand internal flows. Okay. So let's move to the whiteboard. So suppose I have two parallel plates which are separated by a distance 2h. So if I draw the plane of symmetry in between and the y direction starting from here, so y goes from 0 to capital H, so this will be plus h I would say, and let's say this is minus h. So y goes from minus h to plus h in the given y coordinates. And suppose, let's say, the flow enters from this side at a uniform velocity, okay. So there is a uniform velocity profile. So if I draw the velocity profile with respect to y, okay, so suppose this is my y direction and this is my u. It's convenient to plot it this way, okay. So then the velocity at all locations y would be equal at the inlet, okay. So let's say this is a certain velocity called, we can call it as u bar, which is the average velocity over the section. Since the velocity is uniform across the section, the average velocity across the section is also u bar. So since I have now chosen a parallel plates channel into which a flow at a uniform velocity u bar is entering from one end. Okay. Now what will happen as the flow enters the parallel plates channel? Since the plates are stationary and the flow is viscous, the velocity at the plates would become 0, so the flow would stagnate at the flows, and there will be a parallel velocity flow here. So as you go into the channel, there will be a growth of some kind of a boundary layer from both walls, and as you go on, the boundary layer would keep growing until such time the two boundary layers would meet at a certain distance. Let's call this as LD comma h. I'll tell you why the d and h. Okay, so this is a certain length LDH at which the two boundary layers that are developing from both sides would go and meet. Okay. Now we can look upon this as if there are two flat plate boundary layers developing from opposite directions, but there is a small difference. The difference is that the mass that has entered the channel at this end continues to go through this. So if I am looking at the flow at steady state, then at any cross section, this section, this section, this section, or this section, the mass flow rate that is going through is constant. That is, the mass flow rate that is crossing this plane is the same as that crosses this plane, that crosses this plane, that crosses this plane. So we can say that at steady state there is no accumulation of mass inside the pipe or inside the parallel plates channel at any location. Whatever enters leaves. So if the m dot is constant, and that will be equal to the density of the fluid if it is constant, let us say u bar times the area of cross section. So the area of cross section, let me say if I have unit depth in the direction perpendicular to the plane of the board, then the area would actually be 2h times 1. Okay, so this is the mass flow rate that remains constant throughout. So at the inlet this is the mass flow rate, and so that will be the mass flow rate at every location. But now what we have said is that there is a boundary layer development, and therefore the velocity profile at any of these locations, say for example if this is my top wall, okay, the inlet will have a velocity profile as I have shown already in this figure, which is flat. But at a certain distance I'll find, suppose this is my next location, then there will be a velocity profile that will build up like this. So there is a certain region, which is the boundary layer region, where the velocity is less than what it is in the region that is outside the boundary layer. Now if I need to have the average velocity over this section constant, and suppose for a moment let me assume that the density is constant, then this 2h into 1 remains the same, which basically means that if u is less than u bar in this region, because the flow has decelerated because of the presence of the wall, then in this region the u has to be greater than u bar, right? So this is something that naturally flows logically, that if in a parallel plate channel the average velocity remains constant and near the boundaries the velocity is decreased, and then in between, where away from the boundaries, the velocity should increase so that the mean velocity remains at u bar, right? So this is the understanding that we get from here. So if I plot the velocity profile in the form of a box here, so this is the velocity profile here at the inlet. As I go a little further, the velocity profile will look something like this. So in the edges of the boundary layer, up to the edges of the boundary layer, the velocity would have varied, and outside the edges the velocity would remain constant. But that constant, so if I overlay the mean velocity somewhere here, then this region the velocity is less than the mean velocity, and this region the velocity is greater than the mean velocity. So that is the thing that you will get. So if I take an XY plot of this kind and plot all the velocities on one go, I'll get, okay, so this is the lower plate and this is the upper plate, let us say, so this is y is equal to 0. Then at the inlet the velocity profile is this, so this is u versus y, okay. At a certain distance into the plate it would have gone something like this and flat, this, and a certain distance further away it would have gone this and flat, and then eventually you will get a parabolic velocity profile. So the centerline velocity will go on increasing as you go from here up to the point where you reach the two boundary layers meet each other. After the two boundary layers have met each other, there is no further growth, and therefore the velocity profile will become fixed and at all the distances. So as x increases, you go from this to this to this to at this. So this is the kind of velocity profile that you get. The velocity is always 0 at these two locations and the maximum at this location. The centerline velocity will accelerate from u bar to a value which is much higher than u bar at this location. So this centerline velocity, if I call it as uc, the uc would go from u bar at the beginning to some value which is higher than u bar, let us say some n times u bar, where this n is greater than 1. Okay, so this number would go on increasing as we go and finally become a constant. So after the length LDH, then the velocity profile will stop changing any further and you will get a velocity profile which is invariant with time. So what we can say is that in this region from y is equal to 0 to y is equal to LDH, there is a certain flow of, so suppose, okay, let me go to another page and draw the diagram fresh. So suppose this is my parallel plates channel. Okay, so this is the boundary layer that is going from the top boundary and this is the boundary layer that is going from the bottom boundary, and they finally meet at location which is here, and so let us call this as x is equal to LDH and this is x is equal to 0. Then over this distance what happens is the flow that is coming uniformly over the entire section here is actually gradually moving out into the center region. So the mass flow inside the boundary layer region is less as compared to the mean flow, and the mass flow inside in between the two boundary layers, that is the core region if I would call it. So if I can call this as the boundary layer region and the core region of the tube of the parallel plate channel, then in the core region, which is nearer to the center of the channel, the velocity would go on increasing because more and more mass from the boundary layer leaves the boundary layer and comes out to the core, because the boundary layer has restriction on velocities and it cannot carry more mass, and therefore the more and more of the mass moves into this region, and that's the reason why the velocity is at the center between the two boundary layers increases beyond the mean velocity, whereas inside the boundary layer it remains lower than the mean velocity. Okay, and after we reach this location, then the velocity profile becomes a fully developed velocity profile, we call it, and that's why this D, the flow develops from a flat velocity profile to a curved velocity profile. What the shape of that, we will derive it very shortly. So after this velocity remains invariant, so no more outflow of fluid from the boundary layer to core will happen anymore, and the velocities will become independent of x. So u becomes u of x alone in this region, and the u will stop varying with y, and v will actually become 0 because there is no flow perpendicular. So if I call this as u and if I call this as v, the direction perpendicular to the plates is v and direction along the plates is u, the velocity component, then the v component will be present in the region where the flow is moving out of the boundary layer into the core, but will become 0 in the region where the flow is what we call as fully developed. What is fully developed here? The velocity profile, that is the distribution of velocity with y, has become constant. So the velocity profile is developed from what we call as a slug flow profile. The flat profile is called a slug flow profile. Okay, the slug flow is nothing but a constant velocity flow, and here you get a velocity profile which we would be showing that it is parabolic. Okay, so the development of the velocity profile from a slug profile to a parabolic profile happens in the region that is called the entry length of the pipe, or the development length, of the pipe. So the velocity profile develops from the inlet up to the development length, and it's called development length, and that's why LD, and H basically stands for hydrodynamic development length. So LD comma H is called the hydrodynamic development length. Okay, so that's why it's LDH. So from x is equal to 0 to x is equal to LDH is what we call as the hydrodynamic development length, over which the velocity profile undergoes a gradual change, where the velocities inside the boundary layer become lower and the velocities outside the boundary layer become larger, and eventually the boundary layer stops changing shape once the two boundary layers meet at the center line, beyond which you will have a velocity profile which is independent of x, and therefore there will be no velocities in the direction perpendicular to the plates, and there will be only velocities in the direction parallel to the plates. So if I go back to the governing equations, if I write del u by del x plus del v by del y equal to 0, which is the continuity equation or the equation for conservation of mass for two-dimensional flows. In this, if I write the orders of magnitude, then actually v becomes identically 0 in the regions beyond the fully development region. After x is greater than LDH, the v becomes identically equal to 0, and therefore this disappears, which basically then makes del u by del x is 0. So there is no change in u also with x. U becomes a constant with x. Okay, so u is only a function of y, but it becomes independent of x. Del u by del x becomes equal to 0. Okay, so this is basically what you get. So you will get, if I plot y versus u, I'll get a parabolic profile as I showed you. We'll derive that it's a parabola as we go on. So this is plus h and this is minus h. Y is equal to h and minus h, and the velocity goes to u center line, which is the maximum at that location. And this profile now becomes invariant with x. It doesn't change with x anymore. It remains only a function of y after this. Okay, so this is one thing that happens. If I look at the x and y momentum equations, let's look at the y momentum equation first. U del u by del x plus u del v by del x plus v del v by del y is equal to del p by del y with a negative sign 1 by rho del p by del y plus nu times del squared u del squared v by del x squared plus del squared v by del y squared. This is my v momentum equation. Now that v has identically become 0, its x gradient as well as y gradient and second gradient, third gradient, everything becomes 0. So this is 0, and del v by del x is also a 0, and this is also a 0, which basically means del p by del y becomes a 0. The pressure across the section of the duct, does not change. So del p by del y is 0, then p becomes a function of x alone. So you will have del p by del x in the other equation, which becomes dp by dx. The pressure only changes along the length. So there is a drop in pressure from the inlet to the outlet of the pipe because of the frictional losses that happen, the frictional drag that the duct exercises on the water or the gases that flow through the pipe. The pressure only becomes a function of x, and it stops being a function of y. Okay, so now the third equation, which is the x momentum equation, will be u del u by del x plus v del u by del y is equal to minus 1 by rho del p by del x plus nu del squared u by del x squared plus del squared u by del y squared. Now in this, we have already said that del u by del x is 0, and therefore this term goes off. We have said that v is 0, so this term goes off. And since del u by del x is 0, del squared by del x square also becomes 0 because u does not change with x any further. So this is 0. So the only two terms that remain are these two. So that becomes your momentum equation. So your momentum equation is nothing but 1 by rho del p by del x. It has a negative sign, so when I bring it to the left hand side, the negative sign goes away, and this nu is mu by rho. I can write it that way, is equal to mu by rho into del squared u by del y squared. Now we have said that the pressure is only a function of x and u is only a function of y, so the partial derivatives actually disappear. So this becomes dp by dx, and this becomes d squared u by dy squared, because we have said in the previous slide that the pressure is only a function of x and u is only a function of y, and therefore you get dp by dx and dp by dy. So now the density can get cancelled if it is a constant. So what we can say is that this is function only of x and this is function only of y, and if they have to be equal, then they both have to be independently equal to some constant. Okay. So in the fully developed region, therefore, what you say is that the pressure is only a function of x, and it's a linear function of x because dp by dx has to be a constant, and the velocity is only a function of y, and since it is second derivative which is a constant, it actually becomes a parabola. Okay, so this is the equation that we will actually be solving. So suppose I say the duct is here, there is an inlet pressure P and let us say an outlet pressure of 0 relative to, let us say, a standard pressure, let us say the atmospheric pressure. The outlet is at atmospheric pressure and the inlet is, let us say, at a pressure P1. Then the pressure variation in the fully developed region will be a straight line. The pressure will go from P1 to 0 in a straight line in the whole thing. So we can say that dp by dx will actually be equal to P1 minus 0 divided by the length of the pipe when the entire flow is fully developed. Okay, so we have said that, okay, before this the flow is developing, but from this is some value of x which is greater than LDH. Okay, so in this region the pressure will vary in a straight line, and at the exit, if I say the pressure is 0 related to the atmosphere, then at the location where I begin at that x, the pressure, let's say, is P1, then the pressure gradient in this region dp by dx will be P1 minus 0 divided by L. So it's going to be a fixed value of pressure. Okay, and as I increase this difference, the flow would become more and more intense, and therefore the velocity and the velocity gradients will change according to that. Okay. So now, in order to get the velocity profile in the fully developed region, I need to solve this equation, okay, which is u as a function of y, and you'll see that the pressure gradient becomes a parameter there. For a given pressure gradient, there will be a certain flow rate, and the gradients will be according to that. Okay. So now, if I write that equation and try to solve it, then they say d squared u by dy squared is equal to the mu would go from this side to that side, so you would have a 1 by mu dp by dx, and that's a constant. Okay. So now if I integrate this expression, and what are the boundary conditions? The boundary conditions are that you have the parallel plates channel with this is y equal to 0. So at y is equal to 0, the flow is symmetric, and therefore the gradient of u with respect to y has to vanish. Okay, because the flow above it and the flow below it are going to be symmetric about each other, and therefore at y equal to 0, you get del u by or du by dy equal to 0, and at the boundaries, that is at, let's say, y is equal to h, u is equal to 0. Okay, so these are the two boundary conditions to which I am going to solve this expression. So if I solve it, I'll get du by dy is equal to 1 by mu dp by dx, which is a constant, multiplied by y plus, let us say, c1. And if I integrate it the second time, I get u, which is equal to 1 by mu dp by dx which is a constant, so I'll just write it as it is, into y squared by 2 plus c1y plus c2. Okay. Now what we have actually found is, from this itself, if I apply the first boundary condition, du by dy is 0 at y is equal to 0, therefore c1 becomes 0, and therefore I can remove that from here. You get this plus c2 as the equation. Now if I apply the second boundary condition, saying at y is equal to h, u is equal to 0, I will get 0 is equal to, or c2, I can take this to the other side, so c2 would be equal to this with a negative sign, so minus h squared by 2 mu into dp by dx. Okay, so that is your c2. So if I substitute that into this, it's actually y squared by 2 mu here, and so it's actually h squared minus y square. So if I take the h square out, I'll get an expression like this. So u will be equal to minus h squared by 2 mu into dp by dx multiplied by, okay, so you'll have 1 minus y squared by h squared. Is it correct? Because this is y squared by 2 here, and this is h squared by 2 here. Okay, so it's the same, otherwise the rest of the things are same. So if I just keep this outside, so it will become 1 minus y squared by h squared. So this is your velocity profile, and this clearly is an expression for a parabola, and you can see that the dp by dx appears here. So as dp by dx increases, u also increases. So otherwise the shape is, with respect to y, a parabola like this. Now if I substitute y is equal to 0, then I get, so u is equal to minus h squared by 2 mu dp by dx into 1 minus y squared by h squared. Okay, so at y is equal to 0, the quantity is h squared by 2 mu into dp by dx. So at y is equal to 0, u is equal to uc, that's what we said, implies uc is equal to, I can substitute here, so this y becomes 0, it becomes minus h squared by 2 mu into dp by dx. So I can take this as uc then, and if I write it, I get u by uc is equal to 1 minus y squared by h squared is the velocity profile. Okay, and from this I can also find out what is the average velocity. The average velocity will be integral of u dh, actually density being constant, otherwise it would have been, if I take a small segment whose length is, let us say, dx, right, sorry, okay, so if I take at any cross section a small element dy in this region, the velocity at that location is this. So if I have to find out the average velocity, I integrate u dy. Okay, so this should not be dh, it's actually dy. Okay, so if I have to find out what is the average total mass flow rate through this, I'll have to basically integrate rho u dy, because if I take unit depth, then the area of cross section is 1 into dy. So rho into u into area will be the mass flow rate through this elemental region, and if I integrate this from y is equal to 0 to h, I get the mass flow rate that goes through the top half of this one, and if I have to get the average velocity through that, then I'll need to divide it by rho into the top half has an area of h multiplied by unity, so rho h. And if rho is constant, this rho would simply get cancelled out. So I'll get u bar is equal to 1 by h times this. So I can remove the remainder. So the definition for a mean velocity will be u bar is equal to 1 by h integral of u dy from 0 to h. So if I do that integration for this one, then what I'll get is u is equal to uc into 1 minus y squared by h squared is what you have. So if I integrate this, integral of u dy divided by h here, this is integral from 0 to h divided by h is what you get. So if I get the uc by h outside, because uc is a constant, so I can take uc by h outside and integrate this. It's uc by h multiplied by the 1 will get, so this dy, okay, so the 1 will get integrated to y between 0 and h, it will become h minus 0, okay, plus or minus this 1 by h squared will remain as it is, and this will get integrated to y cube by 3, which will be h cube minus 0 divided by 3. Okay, so this is basically what you get. And so if I look at this, then there is a h here and there is a h by 3 here, so it's a h minus h by 3, okay, and that h should also get cancelled with this one, so you will get you get a h minus h by 3, which is 2h by 3, and h would get cancelled, so you get a 2 by 3 uc. So you get u bar, which is actually equal to this, u bar is 2 by 3 times uc, or uc is 3 by 2 u bar. Okay, so what does this show you? You initially started with a uniform velocity u bar here, and when the flow became fully developed, the center line velocity grew to 1.5 times that u bar that you actually got. Okay, so the velocity profile that you write here, you can write this as uc, or you can write it as 3 by 2 u bar. Okay, so your velocity profile will therefore look like u by uc is equal to 1 minus y squared by h squared. This is one way of writing it. The other way of writing it would be u by u bar is 3 by 2 multiplied by 1 minus y squared by square. Okay. So it's the same velocity profile. You are writing either in terms of uc or uh, and they are known to be related to each other using this expression. So what have we got now? We have got the expression for a velocity profile where the mean velocity or the central line velocity is related to the pressure using this expression. So you have uc, which is equal to 2 by 3 3 by 2 u bar, 3 by 2 u bar is equal to minus h squared by 2 mu into dp by dx. Okay, so we'll basically then get u bar, you get the 2 by 3 on the other side, the 2 will get cancelled and 3 will come there. U bar will be actually equal to minus h squared by 3 mu into dp by dx. Okay, so this will be the mean velocity. So as you can see, as the pressure gradient increases, as I increase the gradient of pressure that I impress on the flow, the mean velocity will go on increasing. Okay, and since the mean velocity increases, the mass flow rate through the system increases. Okay, and this will be the relationship, and your pressure drop, your velocity profile is given by 1 minus y squared by u h square with respect to u. So at the center you always have the maximum velocity, and the walls you have a minimum velocity. And we can also find out what will be the expression for pressure drop per unit length. from this we can write that expression. So if I want to write it in terms of the wall shear stress and mean velocity, so I should be able to write that tau wall, which is actually the negative of mu del u by del y at y is equal to h. Okay, and from the expression that I have, which is u is equal to 3 by 2 u bar multiplied by 1 minus y squared by h squared. This is the velocity profile. So del u by del y would actually become at h will be the same 3 by 2 u bar will remain here multiplied by 0 minus 2y by h squared at h. So 2h by h squared is what I get, so it will be minus 2 by h. Okay, so the 2 would get cancelled, so I get minus 3 u bar by h, right? So this is your multiplied by mu, of course. The tau wall will actually be this. This is del u by del y, and therefore mu del u by del y. I'll put a mu here, so you get a mu, right? So that is the expression for this. So with a negative sign, this minus would disappear. So this is actually going to be equal to 3 u bar mu by h. Okay, so that is the expression that I get. So if I write an expression for CF, which is tau wall divided by half rho u bar square, in this case u infinity is replaced by u bar, so the tau wall divided by half rho u bar square, so this will actually become 3 u bar mu by h, and divided by, so this half will become 2 here, and there will be a rho u bar square that you will get. So the square will go with this 1 u, and this rho u bar h by mu is in some form a Reynolds number. Now if I want to write the Reynolds number for a duct like this, the characteristic length should be 2h, and so if I multiply and divide by 2, I get this expression. So this itself is 1 by re 2h. So 3 into 4 into 3 into 2 into 2 is 12 divided by re 2h is the expression that I get. So that is the relationship for the skin friction coefficient as a function of Reynolds number for a parallel plates channel. Okay. So this CF, skin friction coefficient, which is the mean, which is the shear stress at any location divided by this. Now this shear stress is for the fully developed region. Okay, so that is going to be constant with x, and that constant friction factor is going to be 12 divided by re2h. Okay, so that is the friction factor that determines pressure drop at that location. And if I want to write the expression for pressure drop, so if I take the pipe of a certain length where the flow is fully developed in the entire region, so suppose this is my length L, and let's say the area of cross section is A, and let's say there is a pressure P here, and there is a pressure P plus dP here. Okay, P plus delta P. I don't want to write a dP with a finite length. Okay, now the if the shear stress at the boundaries is this toe wall, then the force balance on this would basically tell me that the net force in the positive x direction can be written as P into A minus P plus delta P into A, which will be minus delta P into A, okay, and that will be equal to the shear stress is in the negative direction because the flow is in this direction, shear stress is, so it will be minus tau wall multiplied by the surface area, which will be the perimeter. I'll write it with a capital P, perimeter P multiplied by the length of the thing. So the shear stress multiplied by the area, which will be shear stress multiplied by the perimeter into the length, that force, which is taking the force in the negative x direction, will be equal to the difference between the pressure forces at the two ends. Okay, where this A, now if it is parallel plates channel of width 2h, and if I take the depth to be unit depth, this A would be 2h multiplied by 1. Okay, so this area is nothing but this. And what about the perimeter? The perimeter will be 1 in the top and 1 in the bottom, so this will also be 2. Okay, and what is tau wall? Tau wall, we have already said Cf into half rho u square, so this will be the 2 would get cancelled between these two, and you can actually write minus tau wall into L into half rho u bar square. Okay, so this is your sorry, not so tau wall, it's just Cf. Okay, tau wall is replaced by Cf into half rho u square. So you can take this area to the other side, or let me not substitute for these things as yet, so this remains the way they are. So then this will be perimeter will come here. Okay, so then the delta P will actually be equal to, I can cancel out the negative signs, Cf times L divided by there will be a by P, which is a geometric parameter, multiplied by half rho u bar square. Okay, so this is your expression that you will have. This is actually valid for a parallel plates channel or a circular pipe or whatever geometry it is. So long as the A and P are correctly substituted, they'll this expression for force balance is going to hold good. Okay, so the pressure drop through any pipe with fully developed flow will have a constant Cf and half rho u square. So you will get this expression as the expression for pressure drop. Okay, so this delta P is usually negative, so you will have the expression which kind of gives you as a quantity which is the so the pressure drop, which is the amount of decrease in pressure, will be given by this quantity. So as the flow rate increases, the pressure drop goes as u bar square. Okay, so that is the way the pressure drop would vary. So the pressure drop will increase with the square of the mean velocity that is there in the pipe flow. So this is an expression that we normally use for pressure drops, and in fluid mechanics literature, usually we replace this Cf with a quantity called F, which is actually 4 times Cf. Okay, and this area by perimeter, if I take it for example for a circular pipe, okay, so suppose this is a circular pipe, then the area by perimeter will actually be pi d squared by 4 and divided by pi d. So the pi goes and the d goes, so you get a d by 4. So this actually becomes 4 by d. Okay, so if I write this expression, delta P is equal to Cf times L by d into 4, okay, multiplied by half rho u infinity squared, or u bar squared. Okay, and since this 4cf can be written as f, it can be written as f into L by d into half rho u bar square. Okay, so this is your expression for pressure drop that you would normally get, where this f is called the friction factor, called the Darcy friction factor. Well, this Cf is called the skin friction coefficient. And the relationship between those two is that F is 4 times Cf. This is the relationship that you have. And this F is plotted as a function of Reynolds number in charts which are called the Moody charts, which is available in every fluid mechanics textbook. So what you get is, in the laminar region, this varies as a decreasing function like this. It goes as 1 by Re, and there is a transition region here. In the turbulent region, it goes flat, and you have multiple lines plotted here corresponding to different levels of roughnesses of the wall, because in turbulent flow the wall roughness matters. So as the roughness of the wall increases, then the F value increases at large Reynolds numbers. But as the Reynolds number becomes very large, that is greater than 10 to the power of 6 or so, the F values more or less stabilize to constant values. Okay, so this is something which is available in fluid mechanics textbooks, and usually we use this for finding out the pressure drops when we know the mean flow rates through flow, and therefore mean velocities. Okay, so since Cf is 12 by Re2h for flat plates, the F will actually be 48 divided by Re2h for parallel plates, because it is 4 times Cf. In the same way, we can write it for circular pipes also. For circular pipes, you would be able to get Cf as 16 by Red, where the Reynolds number is defined with respect to the diameter, and therefore F will be actually equal to 64 divided by Red. Okay. So, and the same expression would hold good for the pressure drop, because that was derived without assuming any shape of this one. So the delta P will still be equal to F into L by D into half rho u bar squared, even for a circular pipe, and the friction factor can be obtained from the Moody diagram, which is available in fluid mechanics textbooks. Okay, so this is one element where we understand how fully developed flow has constant friction factor because of the way the velocity profile develops, and the velocity profile becomes independent of x, and therefore you get a constant friction factor, and the constant friction factor can be used to calculate the pressure drops in pipes with fully developed flows. Okay, so this is something that we have understood. Now going back, if you look at the length LED, how do we quantify this LED? We have some information from the boundary layer development for LED. So suppose we say that both these boundary layers are developing from the two ends, and eventually the boundary layer thickness becomes equal to h. Okay, and this distance is LDH. Basically we say that at a distance LDH, x is equal to LDH, the boundary layer thickness is h. Okay, we know that delta by x is equal to, we have said 4.92 divided by Rex to the power of half. Okay, so we can say it's approximately 5 by square root of Rex. Okay, now if I want to substitute, delta is h and x is LDH. Okay, so when delta becomes h, the length x becomes LDH, and that would be approximately equal to 5 divided by RE of LDH to the power of half. Okay, so now this will help us to find out what would be the LDH for a given situation. Okay, so let us rewrite this. H by LDH is equal to 5 is approximately equal to, let us say, 5 divided by rho u, now in this case it is u bar, into LDH divided by mu, and this in square root. Okay, now we would like to write the Reynolds number in terms of 2h. So you multiply and divide by 2h in square root here. So you say 2h by 2h. Okay, so then what do you get? So you multiply here also by 2h, so there will be a 2 into 5 that you get. So what do you get? There is a 2h by LDH on this side is equal to, this is 2 into 5, which is 10, divided by square root of RE2h. Okay, so that is using this term, and this term, and this term. So then that leaves you with a square root of 2h by LDH. Okay, you take the 2h by LDH to the other side, so you get 2h by LDH whole thing raised to the power of, this is 1 minus half, is equal to, or is approximately equal to 10 divided by RE2h to the power of half. Okay, now this is minus half, so if I write this the other way, which is LDH divided by 2h, okay, this whole thing to the power of half. Okay, so this is basically, I am just writing it, this is 2h by LDH to the power of minus half, therefore it is LDH by 2h to the power of half is approximately equal to let me go one step at a time. So it is 2h by LDH, okay, raised to the power of 1 minus half is half, okay, is equal to 10 divided by square root of RE2h. Okay, now if I just take 1 by both sides, so I'll get LDH by 2h, okay, and square both sides is then square root of RE2h divided by 10 the whole square. Okay, will basically then give me is approximately, so then LDH by 2h, which is the development length divided by the distance between the plates on this side, is about 0.01 square root of RE2h. Okay, so this is the expression that you get. Actually, this is an approximate expression, and if we look at the actual solutions or experimental measurements, this comes to something like 0.05. Okay, so normally you get this development length in laminar flow as 5% of the square root of 5% of the RE2h. The square root will disappear because we are squaring it, sorry. Okay, So 5% of Re2H. So if the Reynolds number, let us say, is 100, then this development length will be 5 times the space between the two plates. Okay, and if this is 1000, then it will 50 times the space between the two plates. So that's the estimate of the development length that we have. The same thing also holds good for a circular pipe. Even for a circular pipe, the development length divided by the diameter comes out to 0.05 times the Reynolds number with respect to the diameter. Okay. So that is an estimate of how much distance will you need to travel into the pipe before you find the flow to be fully developed in the case of the velocity profile. Okay. So today we have just gone through the fluid mechanics of flow through an internal flow duct, and we found out that it's akin to two boundary layers developing from two different surfaces and finally merging. Even in a circular pipe, it's quite similar. It's actually like a boundary layer developing from all surfaces and merging into one location as you go. So basically you get the same kind of solution. So instead of the 2h, you will be actually using the diameter of the pipe. So the results are quite similar. That when you travel about 0.05 times the Reynolds number distance, that is the distance LDH divided by the cross-sectional dimension here, either 2h or d, if it is equal to 0.05 times the Reynolds number, then you can expect the flow to be fully developed in the case of laminar flow. In the case of turbulent flow, the flow develops much earlier. We'll talk about that in the next class. So the fully developed flow in terms of velocity profile, so hydrodynamically fully developed flow happens at that kind of a distance, and that increases as the Reynolds number increases in laminar flow. But in turbulent flow, the distance actually varies between 10 to 60 diameters depending on the extent of turbulence. The more the flow is turbulent, the shorter will be the development length, is what we will find. And once the flow is fully developed, we found that the shear stress does not vary with x any further because the velocity profile stops varying with x any further. And the shear stress can be directly related to the flow rate, and the flow rate and pressure drop are related to each other, and using that we were able to derive an expression for the pressure drop through length of a fully developed pipe. So suppose I have a very long pipe, say for example I am looking at calculating pressure drops through water carrying pipelines, let us say in IIT, where you have an overhead tank maybe on the top of the lecture hall complex or the main building, from where the pipes run through the entire lecture hall complex area to all toilets and bathrooms, etc. Then the pressure drop through that pipe can be estimated by neglecting the development length, because the development length will be a few tens to at most a few hundreds of the pipe diameter. So if the pipe diameter is, let us say, 1 inch, then a few hundred inches would be the development length, and the few hundred inches would be hardly a few feet, but the pipe lengths are a few hundred feet or few hundred meters. So the initial length of development can be neglected, and the fully developed pipe pressure drop expressions can be used for calculating the pressure drop through the entire length of the pipe. The entry length will have a slightly higher pressure drop because the velocity gradients are more there at that location, but we can neglect that if that is a very small fraction of the total length of the pipe. So that is a method by which the pipe pressure drops are estimated, and that's a very important calculation required to actually find out how much will be the pumping work required. Say for example, if I want to pump water through a pipe to a certain elevation, then if I have to pump so much of water per unit time through that pipe, then how much will be the pumping power that I will require. So that is something that can be calculated from this pressure drop and the flow rate. The pumping power would be equal to the pressure drop multiplied by the flow rate that goes through it, and that's how you get the power of the pump that is required to deliver it. Okay. So we'll stop at this point. In the next class we'll try to do the thermal development, that is what happens to the velocity, the temperature profile, how does it develop as you go through in a pipe. It's slightly more tricky than the velocity profile, because the temperature profile doesn't become a constant after a certain distance, because heat transfer is still taking place and temperatures are still changing, and therefore it's something else that becomes constant when the flow becomes fully developed thermally, and that's something that we will discuss in tomorrow's class. In today's class, we would have just stopped at the concept of hydrodynamic full development and pressure drops that accrue because of that. Okay. We'll stop here and continue in the next lecture.